Finally, let us address the question of, is the universe really expanding? The reason we think it's expanding is the existence of Hubble's law, and this was generally accepted to be true. However, there are other possibilities, and there is so-called tired light theory, which states that for some reason that as yet is completely unknown, photons coming from very far away lose their energy on the way here in a way that's proportional to the travel distance. There is no physics behind it, but it's a possibility. So several tests have been actually designed to demonstrate that the universe actually is expanding. The first of those is so-called Tolman test, which Tolman and Hubble came up with in the 1930s, and it uses behavior as surface brightness as a function of distance. And here is how it works. If the universe wasn't expanding at all, nothing else funny was going on, surface brightness will be constant, not depending on the distance, because remember, the luminosity declines as a square of the distance, but so does the angular area over which it's distributed, so the ratio of the two remains constant. In tired light theory, the brightness will decline with redshift as first power of 1 plus redshift. And finally, in an expanding universe, it will decline as a fourth power of stretch factor 1 plus redshift. The second method uses time dilation of supernova light curves. Recall that those can be standardized for type 1a supernovae to the same shape. Now these supernovae, or rather their host galaxies, are receding from us with relativistic speeds, and so the clocks are ticking slower there. So we have to compensate for the time dilation. So in addition to the stretch factor that brings them all together, the light curves have to be compensated for time dilation that's proportional to the first power of the stretch factor 1 plus z. And finally, somewhat indirect argument is the black body nature and temperature of the cosmic microwave background. In an expanding universe, the shape of the black body curve is preserved, and the energy density has to scale as the fourth power of temperature. If the universe wasn't expanding, that relationship would not be exactly power of 4. But we do see essentially perfect black body radiation, which is perfectly consistent with an expanding universe. So here is how Tolman test works. In non-expanding Euclidean space, surface brightness is constant and does not depend on distance, because luminosity declines the second power of distance, and so does the angular area over which we're dividing it to get surface brightness. However, in an expanding universe, we have to deal with angular diameter distance and luminosity distance. As you recall, the angular diameter distance is equal to the physical distance divided by 1 plus redshift, because the objects fixed in proper coordinates do not expand with comoving coordinates. And luminosity distance is bigger than the comoving distance by a factor 1 plus redshift, because the photons lose energy and the rate of the photon emission is also dilated. So the upshot of this is that surface brightness will decline as 1 plus redshift to the fourth power relative to what it would be if the universe wasn't expanding. Note that this has nothing to do with curvature of space or anything else. It simply tests whether the universe is expanding or not and assumes that special theory of relativity is valid, and nobody's doubting that. So in some sense, it's completely independent of cosmology, of Hubble constant or all cosmological parameters. In order to perform this test, we need something that can be seen far away that has a constant surface brightness, what we may call standard fuzz. One good choice is the surface brightness intercept of the fundamental plane correlations. Remember, they connect things like radii, velocity dispersion, and mean surface brightness of galaxies in what's essentially perfect correlation modulo the measurement errors. So we can reproject it in such a way that one axis has surface brightness on it, and the intercept on that axis will be defining the standard fuzz. So if we have two clusters of galaxies, one larger distance than the other, and we compare the intercepts for their own fundamental plane solutions, they should shift according to the expansion law. This test was done, and here is the result. This is a log-log plot, so the power law is a straight line, and the line that's drawn through the points here is exactly 1 plus redshift to the minus 4 power. So the universe does really seem to be expanding exactly as Tolman test would say it would. Now the time dilation of supernova light curves. Shown on the left here is a set of light curves as observed they're normalized to the same peak brightness for supernovae of type 1a at different redshifts. On the right, we apply the stretch factor that's normally used to standardize them. However, no correction was made for relativistic time dilation. In the lower left now, we see what happens when we apply the relativistic time dilation correction. The scatter goes way down. And then if we, of course, bin the points, it becomes very obvious. Thus, supernova light curves, as a sense of giant clocks, do behave exactly in the way that should if the universe was expanding. Another way to show this result is to plot this characteristic width of supernova light curves before and after relativistic correction. And before, you can see there is a residual trend. After, the distribution is flat, which means that is the way it should be. So next week, we will start talking about cosmological tests. How do we actually figure out in what kind of universe do we live?